Jai Hind everyone, myself Dr. Bandana Sharma from Ajay Kumar Garg Engineering College. The subject which I am teaching, subject is Engineering Physics, code is KS101T, and the topic which I have started for discussion, topic is electromagnetic field theory. So under electromagnetic field theory, under this topic, we have discussed about displacement current, we have done the modification in Ampere's law. Then we have discussed about our Maxwell equations, which are the base of electromagnetic field theory or electromagnetics. We have tried to understand the significance of these Maxwell equations. Then we have written these equations in integral and differential form. After that, we have discussed the propagation of electromagnetic pulse in free space, and then we have also discussed that electromagnetic pulses they are transverse in nature in free space, means we have proved that electric field vector is perpendicular to magnetic field vector, and electric field vector is perpendicular to direction of propagation, as well as magnetic field is perpendicular to direction of propagation. So up to here we have discussed, and the topic for today's discussion is this one. Today we are going to relate electric field with magnetic field. So in order to derive this relationship, we are going to take the reference of our last lecture. So in our last lecture, in order to prove that the angle between E and H is 90 degree, what I have done, I have taken the cross, I have find the value of del cross E, which was equal to, so give me 1 minute. So what I have done there, I have found the value of del cross E, and when you have solved it, you might have remembered that this was equal to k cross E, right? So del cross E is I k cross E, and since according to Maxwell third equation, del cross E is minus mu naught del H upon del T. So according to the cross product of two vectors, you have substituted the components of del, which is your vector differential operator, and you have substituted the components of E, which is your electric field, and you know what is the value of E. You know that E is E naught e raised to power I k dot r minus omega t, that we have discussed in our last lecture. So after taking that cross product, we have calculated this del cross E, which is I cross E. Then we have substituted the value of H, and then these two equations were equated, and after that the final result which we have got there, that was equal to k cross E is omega mu naught H. So this we have discussed in our last lecture, that is transverse nature of electromagnetic wave in free space, where you have from here you have concluded that since you are having cross product of two vectors, and cross product of two vectors is always equal to a new vector, and that new vector will be equal to that will be perpendicular to both the vectors. So it means this H will be perpendicular to both K and E. So this was the conclusion of last lecture. Now we are taking the reference of this in order to derive the relationship between E and H. So how you are going to derive that relationship, that I will show in this particular slide. So just give me 1 minute. Okay. So according to that third Maxwell equation, k cross E is omega mu naught H. You know what is the meaning of each and every term here. K is your propagation vector, E is electric field, omega is the angular frequency, mu naught is the permeability in free space, and H is magnetic field. So now the next one is, you know that any vector, if you have a vector, then you can write that vector as its magnitude and a unit vector which will give its direction. So any vector can be represented as the multiplication of its magnitude and a unit vector which will give its direction. So using the same logic, I am representing this propagation vector as k, which is the magnitude. K here, k represents the magnitude of propagation vector, and n unit vector that represents the direction of propagation vector. So k into n cross E is equal to omega mu naught H. I hope this is clear that how I am writing this. Now you also know that the angle between that propagation vector and electric field is 90 degree because they are perpendicular to each other. So if you want to write the magnitude of this, then in terms of that magnitude, you can write K E is equal to omega mu naught H, right? So from here, so from this particular equation, you are getting E by H. So this ratio of E and H, that is equal to omega mu naught upon K, right? So up to here, E by H is omega mu naught into K. Now this omega upon K, so this omega upon K, that can be written as the velocity of electromagnetic pulse. So how I am saying that omega upon K is velocity of electromagnetic pulse, that you can understand from here. Omega is angular frequency, which can be written as 2 pi nu, and this K is a propagation vector, and it can be written as 2 pi by lambda. So 2 pi will get cancelled with this, and you know the product of frequency and wavelength, that is always equal to the velocity of that particular wave. So this omega upon K is nu into lambda. So, and you also know, this is equal to nu into lambda, and in free space we have proved that in free space electromagnetic pulse that always travels with c, that is 1 upon root mu naught epsilon naught. It means you can replace this omega upon K, this can be replaced with c, or you can replace that with 1 upon root mu naught epsilon naught. I hope this point is clear. So mu naught is there, and c, you can write c there, or you can write 1 upon root mu naught epsilon naught. Further, after simplification, you are getting this is root mu naught upon epsilon naught. Now you know what is mu naught. Basically mu naught, that is a permeability in free space, and epsilon naught, that is a permittivity in free space. If you substitute the value of these two, you know what is the value of these two constants. This mu naught is basically 4 pi into 10 raised to power minus 7, and this epsilon naught, its value is 8.85 into 10 raised to power minus 12 coulomb square per Newton per meter square. If you will substitute these two values in this under root mu naught epsilon naught, and if you will find that ratio, then this is approximately 377. And if you will see the dimensions of this ratio E and H, then the dimensions are the dimensions of resistance. So this ratio of E and H, in free space, that is basically 377 ohm, and this particular ratio is termed as characteristic impedance. Just give me 1 minute. This is known as characteristic impedance in free space, right? So this E by H is root mu naught epsilon naught, and that is approximately 377 ohm. So you have to remember this. This is a relationship between E and H. You can write this relationship in different forms. You can write E by H as mu naught C. You can write E by H as root mu naught epsilon naught, or 377. You can also write that E is equal to C into capital B. Capital B is magnetic flux density there. So how you can write that? That I am going to show in this slide. At every instant, the ratio of magnitudes of electric field to magnitude of magnetic field in an electromagnetic wave equals to speed of light. How this statement is written? This is according to this. You know E by H is mu naught C. So this E can be written as mu naught HC, and you know what is mu naught into H? Mu naught into H, that is capital V, which is known as magnetic flux density. So you are getting here E is equal to C into V. So the ratio of electric field to this magnetic flux density, capital V, E upon V is equal to C. So this is another way to represent this ratio of E and H, right? So this is the relationship between E and H. The components of electric and magnetic field of plane electromagnetic wave are perpendicular to each other, and they are perpendicular to direction of wave propagation. This we have already derived. We have proved that electric field is perpendicular to K, magnetic field is perpendicular to K, and in addition to that, E and H both are perpendicular to each other, right? So that's all. That is a relationship between E and H here. Now coming to the next topic. So actually the topic which is mentioned in the syllabus, the topic is skin depth. So how you are getting that term skin depth, that we can understand with the help of electromagnetic wave equations in conducting medium. So basically this derivation is not there in your syllabus, but how you are getting that concept of skin depth, that we can only understand with the help of these electromagnetic wave equations. So what you have done in your previous lecture, you have derived electromagnetic wave equations in free space or in vacuum. I am going to follow the similar steps here, right? And after following those similar steps, you will get those electromagnetic wave equations, clear? And using those electromagnetic wave equations, we will try to understand that concept of skin depth, clear? So I am going to start here. So you know, in order to derive the electromagnetic wave equations in conducting medium, so first you should know what is the meaning of electromagnetic wave equations in a particular medium. Electromagnetic wave equation means, if you are saying that electromagnetic pulse is propagating, it means you are talking about wave nature. And in mathematics, if you want to describe wave nature, there should be a second order partial differential equation. And how you are going to get that equation? You should refer that electromagnetic wave equation derivation in free space. So I am following this similar steps here. First step is, you should know what are the Maxwell equations. So that whatever these four equations which are written in front of you, these equations are your Maxwell equations in a particular medium which is having permittivity epsilon and permeability mu. So I am not writing here epsilon naught or mu naught, because if I am saying epsilon naught or mu naught, then these are the permeability of vacuum or free space. But here we are discussing about a certain medium. So I am writing here epsilon as a permittivity of that medium and mu as permeability of the medium. I hope this is clear. So what are these? These are Maxwell equations. And how you are getting these equations? Actually, these equations are differential form of four different laws of electrostatics and magnetostatics that we have already done in our previous lectures. Now this one is, give me 1 minute. Actually, instead of this, here we have conducting medium. So in conducting medium, so this is one mistake, sorry for that. In conducting medium, as you know, the charge will always resides on the outer surface. So in a conductor, if charge always resides on the outer surface, so within the conducting medium, if you will take a small volume element, then there will be no charge enclosed. It means that volume charge density, rho, will be equal to 0 for a conducting medium. So rho is 0 here. And the second one, since you are having a conducting medium, let sigma is the conductivity of that medium. So in terms of that conductivity, you can write the conduction current density as sigma into E. From where I am writing this, you know the microscopic form of Ohm's law, that is your J is equal to sigma into E. So there are two changes. The first change is in first equation, that rho will be 0. In free space, rho is 0, but the reason is different. And the second change will be in this J, and that J will be sigma into E. So I am going to modify these equations for conducting medium. So these are the modifications. First equation is del dot E 0, and you know there is no change in your second and third equation. And the fourth one, instead of J, there will be sigma into E. So these are four Maxwell equations in conducting medium. Now the next step is, in order to find the electromagnetic wave equation, next step is, you have to take the curl of equation number 3 and curl of equation number 4. And after taking the curl of third and fourth, you will get those required equations. So I am going to start with your third equation. So taking curl of equation number 3. So if you are taking the curl of equation number 3, you have to take the curl of left hand side as well as right hand side. So in the right hand sides, you can see here this minus mu is constant, and this del cross, it is a curl operator, and del by del t, it is a partial differential operator, but that is differentiation with respect to t. So minus mu, that is taken outside, and here you are getting curl of del h upon del t. Next step, you know what you have to do. This operator, curl operator, that depends upon x, y and z, and that del by del t, that depends upon time. And these two operators are independent of each other, so you can interchange these. So next one is, you have to interchange these operators. So after interchanging, you can see here you are getting del by del t of curl of h. Why you have interchanged these operators? That I have already mentioned during the derivation in free space, because you know the value of curl of h. So curl of h, that is in conducting medium, it is your sigma E plus epsilon del E by del t. So you have to substitute this value here, and after substitution you will get this. So del cross H is replaced by this. Now next step is this del by del T, this operator will be applicable on both the terms. So you will get here minus mu sigma, after applying this operator on both the terms, you will get minus mu sigma del E by del T minus mu epsilon del square E upon del T square. So you are getting your equation number 5. You know what is the next step? Next step is you have to simplify your left hand side. You have simplified right hand side, and in order to simplify this left hand side, you know this identity, curl of any vector, that is always gradient of divergence of the vector minus del square of the vector. So using the same logic, you are going to take the curl of E, and that will be gradient of divergence of E and minus del square E. And you know, even in conducting medium, this first equation, which is your divergence of E, that is equal to 0. It means your first term will be 0. So that curl of E, that will be replaced by minus del square E. So after substitution, you are getting this gradient of divergence of E minus del square E is equal to this. Now this will be 0. So if it is 0, then you will get minus del square E equals to this, right? So after this, just simplify it and rearrange the terms. So you are getting this second order partial differential equation, right? I hope you remember what is the equation in vacuum or in free space in terms of E. So just to remind you, I am writing the equation here. That equation was del square E minus mu naught epsilon naught del square E upon del T square equals to 0. This was the equation in terms of electric field in free space. So as you can see here, the difference in that free space and in conducting medium is that second term, and in that second term you can see there is conductivity. Sigma is the conductivity of the medium. So because of the conductivity of the medium, you are getting this additional term here. But you can see this is again a second order partial differential equation, right? So this is known as electromagnetic wave equation in conducting medium in terms of electric field, right? So similarly, you are going to derive a similar type of equation in terms of magnetic field. So in order to derive that, you have to take the curl of equation number 4, and you will follow the similar steps, and you will get this equation, del square H minus mu sigma del H upon del T, mu epsilon del square H upon del T square. So you will get this equation. How you will get this equation? After taking the curl of 4. So adopt the similar method and you will get this. So this is known as plain electromagnetic wave equation in conducting medium in terms of magnetic field, right? Now you know that these are second order partial differential equations. So since these equations are second order partial differential equations, and I have mentioned that using the concepts of differential equations or using the mathematical concepts, you can solve those equations and you can find the solution of those second order partial differential equations. And since they are representing the wave nature, so you are going to get the oscillating behavior. So the solution of 7 and 8, that will be of this particular type. So I hope you remember that how you are getting this solution of 7 and 8, since these are second order partial differential equations representing wave nature. So solution will be like this, where E naught is the amplitude of electric field, H naught is the amplitude of magnetic field, K is the propagation vector, omega is the angular frequency. If you remember that in case of free space, you are getting a similar type of solution. But the difference in these two mediums, that is in vacuum and in conducting medium, the difference is this propagation vector K, that is not having a real value, that is having complex value in case of conducting medium. In case of in case of vacuum, K is having a real value, but in case of conducting medium, K is not real, that is having that is a complex quantity. So that is the difference. So in these two equations, K is not real, it is complex, and if you are having a complex quantity, you can represent that complex number as alpha plus I beta, where alpha will represent the real part of propagation vector and beta will represent the imaginary part, right? So these two, alpha and beta, these are the real and imaginary parts of K. So if you will substitute this value of K here, so what you will get? you will get E is E naught e raised to power I alpha plus I beta dot r minus omega t. Now just simplify it. So if you will simplify it, then you will get that this particular term, this will be with iota, and this term iota into iota, that will be iota square or I square, which is minus 1. So you are having this e raised to power minus beta r. So if you will see now, then this particular term, the term which I have highlighted with red color here, so this particular term is basically the amplitude of electric field vector in conducting medium, right? In free space, this electric field is only E naught e raised to power I k dot r minus omega t. This is in free space or in vacuum, and in free space this E naught is always fixed, that is always constant. But if you will see here, this E is E naught into this exponential term, and if you will carefully see this term, this term represents the exponential decay, and in the second term is e raised to power I alpha dot r minus omega t. If you can observe this thing here, that instead of k you are having alpha, means the real part of propagation vector that is playing the role of k, jaisa as in case of free space you are having propagation vector as k there. So the role of k that is played by the real part of propagation vector in conducting medium. And one more change is there, that amplitude of electric field vector is not fixed, is not constant. That amplitude is having this exponential decay term e raised to power minus beta dot r. It means the conclusion is that when an electromagnetic pulse that is propagating in a conducting medium, then when it is moving further into the conducting medium, there will be a decay in the amplitude of electric field as well as magnetic field with the distance. Clear? So next step is, if you will similarly write the expression for magnetic field, it will be H naught e raised to power I alpha plus I beta dot r minus omega t. You will follow the similar steps, and you can see here this is the amplitude of magnetic field vector, again exponential decay. So the conclusion is, so from 11 and 12, the amplitude of electric and magnetic field is, the amplitude of electric field vector is this one, and the amplitude of magnetic field vector is this one. So it means with the increase in distance, as you can see from there, that if r will increase, then this vector, there will be exponential decay. So with the increase in distance, the amplitude of electric field and magnetic field decreases exponentially. Means if this is a conducting medium, suppose this is a conducting medium and electromagnetic pulse is entering into this medium. So if r is 0, means when you are at the surface of that conducting medium, the amplitude of electric field or magnetic field will be maximum, which will be E naught or H naught. And when the pulse is propagating deep into this conducting medium, then with the increase in distance, when it is moving within that medium, with the increase in that distance, there will be exponential decay in the amplitude of electric field or magnetic field. Means there will be this type of exponential decay in the amplitude of electric field or magnetic field. This clear? So at when r is equal to 0, at this point r is 0, so amplitude is maximum. Either for electric field it will be E naught, or magnetic field it will be H naught, right? It means there is an exponential decay in the amplitude. So there will be a certain distance at which the amplitude will become 1 upon exponential times of maximum value. In terms of electric field, E naught, and in terms of magnetic field, H naught. So that particular distance at which the magnitude of electric field is 1 upon exponential times of maximum value, that distance, that particular distance is known as skin depth. So what is skin depth? If this is the surface of conducting medium, then at this point E naught is the amplitude, and if this particular, at this distance, amplitude is 1 upon exponential times of E naught, then this particular distance, this is known as skin depth. I hope the meaning of skin depth is clear. What I am trying to explain here, that if the light is propagating in a conducting medium, then when it is moving into the conducting medium, then the amplitude of electric field as well as magnetic field, that will decrease exponentially. With the increase in distance, it will decay exponentially, right? And at a certain distance, that amplitude will become 1 upon exponential times of maximum value. So that distance is known as skin depth, right? And if you are representing that skin depth with delta, so let delta as a skin depth, it means when r will be delta, means when you are reaching at the skin depth, then this amplitude will be 1 upon exponential times of E naught. So you know what is the amplitude of electric field? I am deriving this relationship in terms of electric field, amplitude of electric field. You can also do the same derivation in terms of magnetic field, right? So EA is E naught e raised to power minus beta dot I. So when R is delta, if you will apply this condition that R is delta, so you know if R is delta, then E amplitude will be 1 upon E times of E naught. Now this E naught will get cancelled. This is e raised to power minus beta delta, which is e raised to power minus 1. If you will compare, you are getting beta delta is equal to 1. So what is the skin depth? Skin depth is basically reciprocal of beta. And what is beta? Beta is the imaginary part of your propagation vector, right? So what is skin depth in conducting medium? Skin depth means when an electromagnetic pulse is propagating in a conducting medium, then there is an exponential decay in the amplitude of electric field or magnetic field with the increase in distance, and there will be a certain distance at which the amplitude will be 1 upon exponential times of maximum value. So that distance from the surface of conducting medium, that distance is known as skin depth, right? And the formula for skin depth is, it is inverse of beta. Now what is beta? Beta is the imaginary part of your that propagation vector. So if you are having a good conducting medium, then this alpha and beta, means real and imaginary part of propagation vector, both will be same, and you can find the value of alpha and beta. So you can solve those quadratic equations and you can find the value of alpha and beta. So I am directly writing the value of alpha and beta here. So up to here I hope everything is clear, that skin depth is inverse of beta, and beta is imaginary part of your propagation vector. So solving the electromagnetic wave equations, the value of alpha and beta can be calculated, and for a good conducting medium, alpha and beta both will be equal and their value will be equal to under root mu omega sigma upon 2. So if this is the value of alpha and beta for a good conducting medium, then what will be skin depth? It is inverse of beta, so it will be under root 2 upon mu omega sigma. So this is the formula for skin depth. So I hope the concept of skin depth is clear. What is skin depth? It is that particular depth from the surface of conductor at which the amplitude of electric field or magnetic field is 1 upon exponential times of maximum value. Clear? So this is the formula for skin depth here. So this is the expression for skin depth in a good conducting medium, right? So I hope this is clear. Now I am going to take our next topic, which is electromagnetic wave equations in non-conducting medium. So we have discussed the electromagnetic wave equations in free space, that is in vacuum. Then we have discussed the electromagnetic wave equations in conducting medium. Now I hope up to now it is clear that how you are deriving these equations. So if you want to derive these equations for non-conducting medium, then we are going to follow the similar steps. So I am just going to tell you those steps, and straight away you can see that how you are getting those equations. So what is the first step? First you have to write Maxwell equations. So these are your Maxwell equations, okay? Right? These are famous Maxwell equations. Del dot E is rho by epsilon, del dot H is 0, del cross E, and I am writing these equations in general form. General form means I am not writing mu naught. If I will write mu naught, then that will be permeability of free space. But here we are dealing with a dielectric or non-conducting medium, so you have to take the permeability of that medium and you have to take the permittivity of the medium. So that's why I am writing here mu or epsilon. Clear? So next step is you have to modify these equations for a dielectric medium or a non-conducting medium. So in dielectric medium, in a perfect isotropic dielectric medium, the properties are same in all the directions, right? And this volume charge density, that is 0 for a non-conducting medium, and since it is a non-conducting or dielectric medium, so J is also 0 here. So there are two changes or two conditions which you have to substitute here. One is rho 0 and J 0. If you will apply these, This one is non-conducting medium. This is non-conducting medium. So if you will write these 4 Maxwell equations for a non-conducting medium, then you are having the change in first equation, that is del dot E0, the second will remain same, third will remain same, and there is a change in fourth equation, that J will be 0. So you are getting these 4 equations here, right? So now next one is that you have to take the curl of equation number 3. You know what are the steps. Take curl of equation number 3, you have taken the curl, then you have interchanged the operators, and after interchanging you are getting this curl of H. You have to replace the value of curl of H, which is epsilon del E by del T. Now after simplifying, the right hand side is this. Now finally you are reaching at equation number 5. Now what is the next step? You have to simplify your left hand side. So if you will simplify it, you will simplify using this identity. Curl of any vector is gradient of divergence of that vector minus del square E. So curl of E, similar logic which you have done in your 2 derivations. So after using the same logic, you are getting this gradient of divergence of E minus del square E equals to this. And you know, in even in a non-conducting or in a dielectric medium, this divergence of E is 0. So if divergence of E is 0, then this first term will give you 0. So you will get only this. And just rearranging, after rearranging these terms, you are getting this second order partial differential equation. If you remember, in free space, the equation was del square E minus mu naught epsilon naught del square E upon del T square equals to 0. This was the equation in free space. You have also done the derivation for conducting medium. For conducting medium, there was an additional term which is minus mu sigma del E by del T minus mu epsilon del square E by del T square equals to 0. And in dielectric medium, you are getting this equation. So you can see the similarity, you can see the differences in these equations. So this equation number 7 is known as electromagnetic wave equation in non-conducting medium in terms of electric field. Now similarly, after taking the curl of equation number 4, after interchanging the operators and after substituting the value of curl of E, you are getting this equation, equation number 8. Similar type of equation. And now what you have to do, you have to simplify your left hand side using the same logic, that curl of A is this. So curl of H is equal to this, and you know, irrespective of medium, divergence of H is always 0. If that is 0, then first term will give you 0. So after simplifying, you are getting this, and just rearrange it in order to get that simplified form. So you are getting equation number 10. What is that? Again, it is a second order partial differential equation, and this equation is for that dielectric or non-conducting medium which is having permeability mu and permittivity epsilon. So this is your plain electromagnetic wave equation in non-conducting medium in terms of magnetic field, right? So next one is, these are the 2 equations, electromagnetic wave equations, one in terms of E and another one in terms of H. And you know, this is general equation, and if you will compare those 2 equations with the general equation, what is the conclusion? Conclusion is this 1 upon V square, that is mu into epsilon. So what is the value of V? That is equal to 1 upon under root mu epsilon. So for a non-conducting or for a dielectric medium which is having permeability mu epsilon, permittivity epsilon, you are having these 2 second order partial differential equations which are your wave equations, and the velocity of that electromagnetic pulse in a non-conducting medium is equal to this, right? So this is your these are your electromagnetic wave equations in dielectric medium or in non-conducting medium. You can also write this as 1 upon under root mu. Mu can be written as mu r into mu naught, and epsilon can be written as epsilon r into epsilon naught. And you know what is 1 upon under root mu naught epsilon naught, which is C, and it is mu r and epsilon r. So you can also represent it as C upon under root mu r epsilon r, where mu r is the relative permeability, epsilon r is the relative permittivity. So I hope the conduction or the propagation of electromagnetic radiations in vacuum is clear, in conducting medium is clear, and in dielectric medium is also clear. So this is these are the equations which will give you that how the electromagnetic pulses, they are propagating in a certain medium. right? Now when these electromagnetic pulses, they are propagating in a medium, they will carry electric energy and magnetic energy with them. So how that energy will flow in a certain medium, that was given by Poynting in terms of Poynting theorem. So the next topic for our discussion, which I will take in next lecture, that is Poynting theorem, and using that Poynting theorem we will derive a Poynting vector, and that Poynting vector is basically represent the intensity of electromagnetic pulse. So that is the topic for next lecture. So that's all for today. Thank you so much.